3. Statistical applications in environmental sciences. Module 8. Measures of dispersion 2 with skewness and kurtosis. Learning objectives. Introduction. Skewness. Kurtosis. Summary. Suggested readings 1. Learning objectives. This module is a continuation of the module, Measures of Dispersion. In this module, Introduction to relative measures of dispersion and different measure of dispersion are discussed with examples. Properties of different measures are also discussed with merits and demerits. There are different relative measures like coefficient of range, coefficient of mean deviation, coefficient of variation, etc. Through this module, one can easily understand about which method to use under what type of conditions. In this module, another important measure like skewness and kurtosis are also discussed. Moments are also introduced here for the derivation of these measures. Questions with detailed solutions are included to give an in-depth knowledge of the topic. 2. Introduction. As measures of dispersion are basically used to discuss about the variation, scatterness of the observations from the central tendency measure. We already covered the one category of measures of dispersion. In this module, second branch of measures of dispersion, that is relative measures of dispersion, will be discussed. Relative measure of dispersion is the ratio of absolute dispersion with its appropriate average, i.e. to find out the relative measure of dispersion from an absolute measure, then the quantity that is used in the denominator must be of same units that of absolute measure. Mostly it is considered as the average. The basic purpose of using these measures over absolute measures that we can compare different dataset, which is not possible with absolute measure due to its dependency on the units. Hence the relative measures of dispersion have a great importance in statistics due to its property of independence of units. Also in the modules, central tendency measures I, central tendency measures 2, and measures of dispersion I, we discussed about different central tendency measures and measures of dispersions. The measures of central tendency and measures of dispersion both together discuss about the characteristics of the dataset, but they are not able to demonstrate that to what extent the observations deviate from the central value, i.e. whether equal number of observations are dispersed from the central tendency or whether the data is symmetrical about the mean or not. Therefore it does not answer how many observations have their value below the mean value or above the mean value. If one is interested to know about the concentration of the observations around a central tendency measure, then it is. 4. Statistical applications in environmental sciences. Essential to study 2 more measures. These are skewness and kurtosis. These 2 measures are considered as a supportive measures for better understanding the characteristics of the data. Skewness is basically used to tell about the shape of the data, i.e. whether data is symmetric or skew-symmetric. Skewness value help in determining the concentration of the observations below and above the average value. If the observations are concentrated in the center, then it is called symmetric. If the observations lie on either side of concentration of observations, then there are 2 possibilities, either more than average value or less than average value. Hence there are 2 types of skewness for asymmetric data, i.e. positive or negative depending on the concentration of the observations. We will discuss about it later. Another important measure is kurtosis, which refer to the peakness, flaterness of the curve that can be drawn from the dataset. It is basically used to study the concentration of the observations at the central part is whether more or less. If the concentration of observations at central part is very high, then the curve is leptokurtic. On the other hand, if the concentration of the observations at the center is less, then the curve is platykurtic. Hence central tendency measures, measures of dispersion, skewness and kurtosis represent a complete package to understand the data in depth. In other words, it completely describes the distribution of the data. Relative measures. Relative measures. A coefficient of range. This measure of dispersion is evaluated from the range of the data set. First range of the data set is calculated, then coefficient of range equals H minus LH plus L, where H is the highest value in the dataset. L is the lowest value in the dataset. B. Coefficient of quartile deviation. This measure is defined as the ratio of quartile deviations to its average value. It is defined as coefficient of quartile deviation equals Q3 minus Q1 Q3 plus Q1, where Q1 is the first quartile, Q3 is the third quartile. Case 1. Find out the quartile deviation from the following dataset related to the marks obtained by 15 students in statistics. 60, 67, 56, 78, 92, 55, 72, 54, 49, 59, 37, 84, 83, 69, 62. Hands. Arrange the observations in the ascending order. 37, 49, 54, 55, 56, 59, 60, 62, 67, 69, 72, 78, 83, 84, 92. 5. Statistical applications in environmental sciences. Compute the range that is 92 to 37 equals 55. Coefficient of ranges equals 55. 129 equals 42.63%. Now compute the first quartile plus 1. 4. Th term i.e. 55. Similarly, third quartile is 12th term i.e. 78. Quartile deviation is 78 to 53. 2 equals 25 halves equals 12.5. Coefficient of quartile deviation equals 25. 131 equals 19.08%. Hence coefficient of range and coefficient of quartile deviation is 42.63% and 19.08% respectively. See coefficient of mean deviation. This relative measure of dispersion is derived from the mean deviation. Mean deviation is computed as the absolute value of difference of observations from a central tendency, i.e. mean, median and mode. Mostly, mean deviation is calculated by taking deviation of observations from mean and median. So in order to convert the mean deviation measure into independent of unit, coefficient of mean deviation is computed. Coefficient of mean deviation equals mean deviation. Central tendency measure. Central tendency measure can be mean or median, but it is divided by the measure that is used for the derivation of mean deviation or from which the mean deviation is derived. Case 2. Calculate the coefficient of mean deviation about mean for the following dataset. Observations frequency. First, compute AM of the data using the formula n area summation FIXI. N, where n equals n area summation FI. The values are shown in the table 2. Column 4 shows the difference of each observation from its mean value. Column 5 is the modulus of values derived from column 4. Now multiply this absolute value with the corresponding frequency. Compute the AM of these absolute observation. Mean deviation of the observations is evaluated as 8.2278. 6. Statistical applications in environmental sciences. To compute coefficient of mean deviation, divide the mean deviation value with the mean, that is coefficient of mean deviation equals 8.2278. 50.65 equals 16.2. 50.65 equals 16.24%. Hence the mean deviation and coefficient of mean deviation is evaluated as 8.22 and 16.24% respectively. D. Coefficient of standard deviation. As standard deviation is evaluated in terms of the observation's units and is considered as an absolute measure of dispersion. It is essential for the comparison purpose that the measure must be independent of units. The relative measure based on standard deviation that is independent of units is called coefficient of standard deviation. It is defined as coefficient of standard deviation equals sigma x, as coefficient of standard deviation would be given in fraction. So if we want to express our coefficient value in term of percentage by multiplying the coefficient by 100, then this relative measure is called coefficient of variation CV. It is defined as coefficient of variation equals sigma xx 100. The coefficient of variation is among the most popular relative measure of dispersion. It is basically used to compare the variability among two or more dataset. The dataset that has more value of coefficient of variation among two is said to be more variable and vice versa. 7. Statistical applications in environmental sciences. Case 3. Calculate the coefficient of standard deviation and coefficient of variation for the following dataset. Observations. Take square. Now take square. Calculate the mean of the observations as shown in table 3. Subtract the mean from the observations as shown in fourth column. Now take square of these observations as shown in the fifth column in table 4. Column 6 shows the product of frequencies with values from column 5. Now take sum of the observations in column 5 and divide it by NIE total frequency. Take square root of the value 125.22 and the standard deviation value is 11.190. Observations. XI. Frequency. Mean. N area. N equals. Table 4. Now for the coefficient of standard deviation, the formula is 8. Statistical applications in environmental sciences. Coefficient of standard deviation equals. For the coefficient of variation, the formula is 50. Hence, we discussed about different relative measures of dispersion, as these measures are derived from the absolute measures to make them independent of units. So one should know about absolute measures of dispersion in depth and the properties before applying these measures on the dataset. Now, in the next session, we will discuss about the skewness and kurtosis. 3. Skewness. A skewness is basically to see tendency of the shape of the distribution. If the frequency distribution of the data is not equally distributed about the mean, i.e. the frequency distribution is not symmetric, then the term that is used to refer this situation is called skewness. Skewness has many synonyms like asymmetry and lack of symmetrical. Some authors give definitions of skewness as, when a series is not symmetrical, it is said to be asymmetrical or skewed, by Croxton and Cowden. Measure of skewness tell us the direction and the extent of skewness. In symmetrical distribution, the mean, median and mode are identical. The more the mean moves away from the mode, the larger the asymmetry or skewness, by Simpson and Kafka. Hence skewness means that the data is not symmetrical about the mean. It is also be defined in term of normal distribution. Normal distribution is the distribution which has mean, median and mode all are equal. Hence the shape of the frequency of this distribution is like bell shape. 9. Statistical applications in environmental sciences. Figure 1. Link for the image. Hence from the figure 1, one can observe the shape of the frequency distribution. A frequency distribution is said to be positive skewed when the mean, mu greater than median greater than mode. In this case, the value of mean is more than the value of median in mode. Also median value is more than the value of mode. A frequency distribution is said to be symmetric distribution when the mean, mu equals median equals mode. In this case, the values of mean, median and mode all are same. A frequency distribution is said to be negative skewed distribution when the mean, mu less than median less than mode. In this case, the value of mode is more than the median and mean. Also the median is more than the mean. Difference between skewness and measures of dispersion. As we discuss above different measures of dispersion, as dispersion measures are basically used to know about the variation in the dataset while skewness is concerned with the concentration of the observations around the central part of the data. There are some important differences between measure of dispersion and skewness. These are, skewness is basically concerned about the shape of the frequency distribution while measures of dispersion are more concerned about the amount of variations. Skewness shows the nature of data about its central value while dispersion try to measure up to what extent the central tendency value represent the whole data set. It is possible that the data that is more dispersed but has symmetric frequency distribution. Hence in that case one can say that symmetric does not mean that variation is less. 10. Statistical applications in environmental sciences. IV measure 10. 10. Statistical applications in environmental sciences. IV measures of dispersion are based on first and second order moments while skewness is based on first, second and third order moments. This is the reason that both skewness and measures of dispersion are studied together in literature, as both measures help in understanding the features of the frequency distribution in depth. There are many methods available in the literature to find out the skewness. Some of them are discussed here. Measures of skewness are used to detect whether the frequency distribution is symmetric or skew, as the values of these measures depend on the units of the observations. So there are two categories of measures of skewness. These are a. Absolute measure of skewness. B. Relative measure of skewness. Absolute measures of skewness. These measures of skewness are basically used to check the asymmetry of the data. Hence these measures assume that the data is not symmetric, otherwise the values of these measures will be zero. Some of the measures of skewness are given below. A. Mean, mu minus mode MD. B. Mean, mu, median M. C. Q3 plus Q1 minus 2M. Hence by using the above three measures one can check the skewness of the distribution. As we already discussed that in skewed distribution either the mean value is greater than median or mode is greater than median and mean. Hence, these measures just give you an indication about the presence of skewness in the data. Expect when the value of these measures is zero, in that case data is symmetric. However, these measures of skewness have limited utilization in practice due to these reasons. These are the first and the most important thing is that these measures are based on the units of the observations. Hence the values that are derived from these measures cannot be used for comparison purposes. If absolute measure of skewness values of two datasets are same. It does not mean that dataset are always same, as it may be possible that there may be variation between distributions in terms of mean and dispersion. Now to overcome these limitations, another measure that is independent from units is used is called relative measure of skewness or coefficient of skewness. 11. Statistical applications in environmental sciences. Relative measure of skewness. In these measure, the limitations of absolute measures have been removed by dividing the absolute measure by the suitable measure or quantity. The following are some coefficient of skewness which are commonly used. A. Carl-Pearson coefficient of skewness. The formula for Carl-Pearson coefficient of skewness is given as coefficient of skewness equals mean minus mode. Standard deviation equals 3 mean minus median standard deviation. B. Bowley coefficient of skewness. The formula for Bowley coefficient of skewness is given as coefficient of skewness equals Q3 plus Q1 minus 2 median. Q3 minus Q1 where Q1 are the third and first quartile of the distribution. C. Kelly's coefficient of skewness. The formula for Kelly coefficient of skewness is given as coefficient of skewness equals D9 plus D1 minus 2 median D9 minus D1. Where D9, D1 are the ninth and first deciles of the distribution. D. Measures of skewness based on moments. D. Measures of skewness based on moments. This measure of skewness is the most widely used method. Here the measure used second and third order moments about mean. This measure is defined as coefficient of skewness equals mu3 sigma 3, where mu3 and sigma are the third order moment and standard deviation of the distribution. Case below 54, 63, 7. Hands arrange the series in ascending order. 12. Statistical applications in environmental sciences. Now compute arithmetic mean, median and mode from the series. A.M.is 69.33, median is 69, mode is 63. Mean mu minus mode MD equals 69.3. We need let x1. We need Now calculate the relative measures of skewness. We need standard deviation of the data. Let x1, x2, xn be the observations and n is the number of observations. SD is evaluated by using the formula S D sigma equals square root n area summation xi minus x2. N equals 14.079. Carl-Pearson coefficient of skewness is coefficient of skewness equals 69.33 minus 63. 14.079 equals 0.4496. Bully coefficient of skewness is. Coefficient of skewness equals Q3 plus Q1 minus 2 median. Q3 minus Q1 equals 85 plus 58 minus 2 asterisk operator 69. 85 minus 58 equals 0.1851. Kelly coefficient of skewness equals D9 plus D1 minus 2 median D9 minus D1. Sigma 3 equal 214. Hence from all the absolute and relative measure of skewness, we conclude that data is positively skewed. Although we also notice that different measures have different values for same dataset, that is considered as the limitation of the measures of skewness. 13. Statistical applications in environmental sciences. 4. Kurtosis. Kurtosis word comes from the Greek language with a meaning curved arching. Kurtosis is basically used to measure the peakness of the frequency distribution. It is possible that two dataset have same arithmetic mean, standard deviation and coefficient of skewness, but still one has different concentration of values near the mode value. So the distribution can have more peakness than the usual normal distribution, less peakness than the usual normal curve, and equal to the normal distribution curve. So basically kurtosis is a measure that compare the peakness of the curve relative to the peakness of a normal curve. So kurtosis is basically used to measure the extent how the distribution is more peaked or less peaked than the normal distribution curve. Many authors give the definitions of the kurtosis as: a measure of kurtosis indicated the degree to which a curve of a frequency distribution is peaked or flat-topped, by Croxton and Cowden. Kurtosis is the degree of peakness of a distribution, usually taken relative to a normal distribution, by Spiegel. Figure 2. Courtesy for images wettlearn.wikia.com. So if the distribution curve, blue curve, is more peaked than the normal distribution is shown with blue curve in figure 2, then the distribution is called leptokurtic. If the distribution curve, red curve, is more flat than the normal distribution curve, then the distribution is called platykurtic. Hence, the black curve represent the normal curve is also known as mesokurtic. 14. Statistical applications in environmental sciences. Measure of kurtosis. Kurtosis is defined as beta 2 equals mu 4 sigma 4, where mu 4 is the fourth order moment about mean. Sigma is the standard deviation. If beta 2 greater than 3, then the distribution is leptokurtic. If beta 2 equals 3, then the distribution is mesokurtic. If beta 2 less than 3, then the distribution is platykurtic. Another measure that is used in literature is gamma 2 equals beta 2 minus 3. Hence in this case, if gamma 2 greater than 0, then the distribution is leptokurtic. If gamma 2 equals 0, then the distribution is mesokurtic. If gamma 2 less than 0, then the distribution is platykurtic. Case 5. Calculate the kurtosis of the marks of 15 students in statistics given below. 54, 63, 78, 59, 69, 74, 85, 46, 63, 51, 58, 73, 86, 88, 93. ANS SD of the data is evaluated as 14.079. Mu 4 equals N area summation xi minus x4. N equals 71,641.5407. Kurtosis is beta 2 equals mu 4. Sigma 4 equals 71,641.5407. 14.0794 equals 1.8233 less than 3. Also gamma 2 equals beta 2 minus 3 equals 1.8233 minus 3 equals minus 1.177 less than 0. Hence the distribution is platykurtic. 15. Statistical applications in environmental sciences. 5. Summary. In this module, first we introduce the relative measures of dispersion. There are different relative measures like coefficient of range, coefficient of mean deviation, coefficient of variation, etc. Properties of different measures are also discussed with merits and demerits. Difference between dispersion and skewness are also discussed. Through this module, based on the merits and demerits, one can easily understand about which method to use under what type of conditions. In this module, another important measure like skewness and kurtosis are discussed. 4. Statistical applications in environmental sciences. 1. Learning objectives. The objective of this module is to introduce key concepts that help to understand probability problem in simple words and different approaches to find numerical measure of probability for different probability problem. Examples and some images are used for better explanation of this topic in an easy manner. 2. Introduction. Probability measures the uncertainty of an event in an experiment. Theory of probability is an important branch of mathematics and statistics that provides numerical measure of the probability. Probability is also used in our daily life. Likely, possible, high chance of use of like words in day-to-day life to express uncertainty of happening an event. For example, possibly, it will rain today and there is a high chance to get my dream job in next 2 months. According to Yao-Lin Cho, probability is the science of decision-making with calculated risks in the face of uncertainty. Probability phenomenon is mostly observed in business, economics, social science, daily life and actuaries. Probability has many application in economics, business and actuaries because there are terminologies such as risk, taxes, profit, loss, etc. These terminologies express uncertainty of an event under an experiment. Suppose an investor invests money in money market. There are chances that either investor will get more money as profit of investment or will face loss in the investment. This shows uncertainty. Probability terminology can be used here. A real-life exercise of number plate of Victorian is shown in figure 1. You will be able to solve these types of exercises after completing this module on probability. 5. Statistical applications in environmental sciences. Figure 1. 3. Terminology. Terminology. There is a need to be aware about some basic concepts of probability before going to numerical measure of probability. In this section, focus will be on key concepts to understand a probability problem in words and convert into numerical form to solve it by using different approach of probability according to the features of the problems. Key concepts are given as 3.1 Random experiment. Before conducting an experiment, there is no possibility to get outcome of any problem. Experiment is a process to observe an uncertainty in the problem. Random experiment is an experiment in which outcome of an trial or event under some identical circumstances are not unique, but it will be among all the possible outcomes. List of some examples of random experiment is given below. Tossing a coin. Rolling a dice. Observe risk of an investor. Selecting a card from a deck of cards. Selecting a ball from a group of balls. 6. Statistical applications in environmental sciences. Arrangement of persons in a queue. Observe the number of Xiaomi Android phones sold by Amazon in 2017. Selecting a student from a classroom. Observe the number of wickets in a cricket match. Observe product of a process in a manufacturing company. Observe a bulb is either fuse or not. Observe a person who speaks either truth or lie. Observe the number of car accident in particular place. Observe the number of birth in India in year 2017. Observe the share market prices. 3.2 Outcome. After conduct of a random experiment, now to observe the uncertainty of a problem, there will be some results or outcome of that experiment. Outcome gives us an idea about all possible results of that experiment. Outcome is a result of a random experiment. List of some outcomes of random experiment is given as outcome of tossing a coin, head H or tail T. Outcome of rolling a dice, 1/2, 3/4, 5/6. Outcome of selecting a ball from a group of different colors, balls like blue, red, white, blue, red, white. Outcome of risk of an investor, high risk, neutral risk, low risk, no risk. Outcome of selecting a card from a deck of cards, 1 2/3. 10 JQKA club, spade, diamond, heart, red, black. Outcome of working condition of a bulb, fuse, not fuse. Outcome of a person speaking tendency, truth, lie. Outcome of observing car accident in a state, 1 2. Outcome of product quality in a manufacturing company, defective, non-defective. 7. Statistical applications in environmental sciences. 3.3 Sample space. After identifying the result of the experiment, there is a need to arrange all possible outcome. In basic mathematics, the definition of set was described. Set is a group of well-defined objects that related to each other under same consideration. Here, result of an experiment is well-defined different result under same consideration, so set is used as sample space to arrange all possible outcomes. Sample space is set of all possible outcomes of an experiment. List of some examples of sample space are sample space for tossing a coin, HT. Sample space for rolling a dice, 1, 2, 3, 4, 5, 6. Sample space for selecting a card from a deck of cards, 1, 2, 10, A, K, Q, J. Sample space for selecting a ball from a group of balls of different color like blue, green and red, blue ball, green ball. Sample space of observe risk of an investor, high, low, neutral, no. Sample space of product that produces by a manufacturing company, defective, non-defective. Sample space of observe a bulb, fuse, non-fuse. Sample space of observing person talk, truth, lie. Sample space for observe car accident in a state, 1, 2, 3. Sample space for observe the number of wickets in a cricket match, 1, 2, 22. 3.4 Event. If one is interested in particular results among all possible results of a random experiment, these particular results can be obtained in terms of events. Event is a particular performance of a random experiment. List of some examples of event. Suppose a random experiment is tossing a coin 2 times. Sample space, HH, HT, TH, TT. Possible event. Getting head both times, getting tail both times, getting one head and tail of a coin. Suppose rolling a die 2 times is a random experiment. 8. Statistical applications in environmental sciences. Sample space, 1, 1, 1, 2, 1, 6, 2, 1, 2, 2, 2, 6, 3, 1, 3, 2, 3, 6, 4, 1, 4, 2, 4, 6, 5, 1, 5, 2, 5, 6, 6, 1, 6, 2, 6, 6. Possible event. Getting same number both times, getting odd number at first time and even number at second time, getting odd number at first time, getting sum of both as even, getting sum of both time as odd, many more event may occur. Selecting a card from a deck of cards is in random experiment. Sample space, 1, 2, 10, A, K, Q, J. Possible event. Getting a spade, getting a club, getting a heart, getting a diamond, getting a face card, getting a king, getting a queen, many more event may occur respect to sample space of random experiment. 4. Types of events. There are many types of event according to the happening of event and outcome. In this section, types of event are defined. 4.1 Simple event. Suppose a particular event happens among all possible events. Result of particular event is at most 1, then event is called simple event. An event that shows exactly one outcome of a random experiment is a simple event. Example. Suppose a quality analyst analysis 2 processes product in a random experiment and classify the process product as defective product and non-defective product. Sample space. NN, ND, DN, DD. Where D is for defective product and N is for non-defective product. Let E is an event. Event E. Neither product is defective. E equals NN as E has only one outcome. E is a simple event. 9. Statistical applications in environmental sciences. Example. Tossing a coin 2 times in a random experiment. Sample space. HH, HT, TH, TT, where H represents head, T represents tail. Let E be an event, getting head both time. E equals HH. E has only one outcome. E is a simple event. 4.2 Compound event. Suppose a particular event happens among all possible events. Result of particular event is at least one outcome. That event is called a compound event. A event shows more than one outcome of a random experiment is a compound event. Example. Suppose a quality analyst analysis 2 processes product quality in a random experiment and classify the process product as defective product and non-defective product. Sample space. NN, ND, DN, DD. Where D is for defective product and N is for non-defective product. Let E is an event. Event E. At least one product is defective. E, ND, DN, DD. E has more than one outcome. So, E is a compound event. Example. Tossing a coin 2 times is a random experiment. Sample space. HH, HT, TH, TT, where H represents head, T represents tail. Let E be an event, getting head at least one time. E, HH, HT, TH. E has more than one outcome. So, E is a compound event. 4.3 Exhaustive event. 10. Statistical applications in environmental sciences. All possible results of an experiment is termed as an exhaustive event. Exhaustive event is the total outcome of a random experiment. List of some examples are. Tossing of 1 coin is a random experiment. Exhaustive cases are 2. Throwing a dice. Exhaustive cases are 6. Throwing 2 dices. Exhaustive cases are 62. Tossing 2 coins. Exhaustive cases are 22. Selecting a card. Exhaustive cases are 52. 4.4 Dependent event. 2 particular events E and F occurred in a trail. Result of one event are affecting the result of second event. Event may be either E or F. These events will be dependent event. Event is said to be dependent event if happening of one event in one trail is affected by happening of similar event in next trail. Examples. Drawing a card from a pack of card followed by one after another draw is a random experiment. Let us consider E as an event of drawing black card. If first drawn card is not replaced in the deck of card while second card is drawn, then the second time drawn card will be dependent on the first drawn card. After this, total number of cards are decreasing followed by one after another draw. So, E is a dependent event. Let us consider a bag with 5 marbles, 4 are red and 1 is blue. If a marble is selected at random from the bag and not replaced again into the bag, the chance of occurrence of the blue ball will keep increasing with each consecutive draw. 4.5 Favorable event. Outcomes of a particular event are favorable to that events. These outcomes of events are considered as favorable event. 11. Statistical applications in environmental sciences. Favorable event is the number of outcome favor to an event. Examples. Tossing 2 coins is a random experiment and getting head on both coins is an event. Exhaustive event is 22 equals 4 and favorable event is 1, i.e. head and head. Throwing 2 dice is a random experiment and getting same number on both sides is an event. Favorable event is 6, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. 4.6 Mutually exclusive event. Events can't occur simultaneously in same trial or mutually exclusive events. Suppose A and B are 2 events. If A and B are mutually exclusive event, their Venn diagram is given in Figure 2. Figure 2. Examples. Head and tail are 2 outcomes of random experiment of a coin. Suppose A and B are 2 events of getting head and getting tail respectively. Both event cannot occur in a single trail, so A and B are mutually exclusive event. 1, 2, 3, 4, 5, 6 are the possible 6 outcome of random experiment in throwing a dice. All of these outcomes cannot occur in a single trail, so they are all mutually exclusive event. A switch cannot be on, off at same time. Switching a switch button is a random experiment that has 2 possible outcomes on and off that switch is on while the second one shows switch is off. Both event cannot occur at same time, so A and B are mutually exclusive event. 12. Statistical applications in environmental sciences. 4.7 Independent event. 2 particular event E and F are occurred in a trial. Result of one event is not affecting the result of second event. Event may be either E or F, so these events will be independent event. Event is said to be independent event if happening of one event in one trail is not affected by happening of similar event in next trial. Examples. Throwing a dice is a random experiment. If one gets 6 in first throw as well as in second throw, one can see that both throws of a dice are not affecting the outcome of each other, so these are independent event. Tossing a coin is a random experiment. If one get head on first toss as well as second toss, one can see that both tosses of a coin are not affecting the outcome of each other, so these are independent event. Drawing a card from a pack of card with replacement is independent event. Every time total number of cards remain same. 4.8 Equally likely events. All possible event of a random experiment have same numerical value of probability of occurring events. These events are known as equally likely events with equal probability of occurrence. Equally likely events shows equal probability for all events. There is no preference for any event, all have equal preference. Example. Tossing a coin is a random experiment. Possible outcomes are head and tail. Possible event are getting head and getting tail. One has total possible outcome is 2. Probability of getting head is 1/2. Probability of getting tail is 1/2. Both have equal probability and equal preference. So, events are equally likely events. 13. Statistical applications in environmental sciences. Example. Throwing a die is a random experiment with 6 possible outcomes and events. All possible events have equal probability, i.e., 1/6. So all events have equal preference to happening, known as equally likely events. 4.9 Impossible event. If an event under a random experiment cannot occur, that event is known as an impossible event. Numerical measure of an event is 0, then the event is impossible event. For an impossible event P equals 0. Example. If tossing a dice is a random experiment, E is an event of outcome greater than 6. We know that dice have 6 faces only, so there is no chance of happening this event. Hence event E is an impossible event. 4.10 Certain event. If there is an absolute surety on the chance of occurrence of an event is known as certain event. Suppose if it is Thursday, the probability that tomorrow is Friday is certain event with 1 probability. Numerical measure of an event is 1, then event is certain event. For a sure and certain event P equals 1. Example. 14. Statistical applications in environmental sciences. Hitting a dart is a random experiment and throwing a dart at center is an event on the dartboard. Imagine that this is only one thing in the universe and dart hit at the center. There is only one chance to throw, then this event is sure event. 4.11 Complementary event. Non-happening of an event A is known as complementary event and it is denoted by AC. Sum of happening and non-happening event will be 1. PA plus PAC equals 1. Example. Tossing a coin is a random experiment and we are interested in getting head. If head appears, then it is a happening event. Getting tail is non-happening event and complementary event. Rolling a dice is a random experiment and getting 6 on dice is event. Getting value other than 6 or not getting 6 is non-happening event and complementary event. 5. Probability approach. After understanding the statement of the problem, next move is to calculate the numerical value of uncertainty. To calculate the numerical value of the probability, several types of approach and methods available in the theory of probability. Some of them are discussed here. Most of the time, 3 types of approach are used to solve probability problem in numerical form. In this section, these 3 approach are defined. Basically, 3 approach of probability are also used as a definition of the probability. A. Mathematical approach. This definition of probability given by James Bernoulli, who was the first person of obtaining numerical measure of uncertainty. This definition of probability is also known as classical a priori probability. If F denotes the favorable outcome of an event E of a random experiment and T denotes the total possible outcome. The probability of happening an event E is given by P equals number of favorable outcome total number of possible outcome equals F T. 15. Statistical applications in environmental sciences. Note, all possible outcomes in mathematical approach must be exhaustive, mutually exclusive and equally likely. Example. Suppose a random experiment of randomly selecting a card from a deck of cards of 52 has equally likely outcomes. Let event A equals king probability of an event A equals 4 50 seconds. B equals jack, queen, ace probability of an event B equals 12 50 seconds. Favorable outcomes are 4, 12 on both event. B. Statistical approach. Probability of happening an event E under a random experiment performed repeatedly under regular and identical circumstances is the ratio of the number of times event occurred to the number of trial. This limit must be unique and finite. Probability of happening event E given by P equals number of event outcome number of trial equals N. This approach of probability is also known as empirical approach of probability due its repetitive behavior. Example. A survey conducted in Batinda district of Punjab state to observe that how many people wearing helmets are not. Total population of Batinda district is approximately 285,813. Let the 40,000 use regularly helmet. Probability of use of helmet on regular basis is 40,285,813 equals 0.139951. C. Subjective approach. Subjective approach is completely biased. Numerical measure of this approach cannot be possible because it is based on biasedness, based on person's knowledge, beliefs, experience and intuition. Suppose one old person assumes the chance of cold in winter will be normal and not too cold. One businessman observes the chance of no profit in the business this year. 16. Statistical applications in environmental sciences. Above example of subjective approach will vary person to person. This approach is not quite enough to measure probability numerically. 6. Axioms of probability. Numerical measure of uncertainty to respective event is called probability. For accurate and best result of an event as much as possible, probability must follow some axioms. Axioms of probability are given as axioms of non-negativity. Probability of an event must be non-negative. Suppose E is any event of a random experiment, probability of E is PE is greater than or equal to 0. Probability lies between 1 and 0. Probability must be non-negative but less than 1. 0 is less than or equal to PE is less than or equal to 1. B. Axioms of certainty. Probability sum of all possible outcomes of a random experiment must be 1. Suppose E is an event of a random experiment, probability sum of all possible event is PE equals 1. If probability of getting head at first time of tossing a coin is 0.5 and probability of getting tail on first time of tossing a coin is 0.5. Total of getting head or tail is 1. C. Axioms of additivity. Probability of union of all events is equal to the sum of the probability of all distinct event. P n airy union AI. N. I equals 1. Equals n airy summation P AI. N. I equals 1. Where AI are mutually exclusive and exhaustive events for all I equals 1, 2, 3, 4, n. 17. Statistical applications in environmental sciences. 7. Permutations. If a probability problem is related some specific type arrangement like arrangement of letter of a word, arrangement of persons in a queue, etc. Permutations are used to solve these type of arrangement problem. Mathematical form of permutation. Special arrangements of items defined by permutations. When selecting m items from the n items, possible permutations are given by this formula. Pm. N equals n. N minus m. Where n minus m equals n minus m minus 1. 1. Example. Possible permutations of selecting 2 vowels from the 5 vowels is 5. 5 minus 2 equals 5. 3 equals 20, as we have 5 vowels, so the possible permutations is 20. 8. Combination. If a probability problem is related to selection of some unit from a huge amount of same unit like selection a ball from a bag, selecting a card from a deck of card, etc. Combinations are used to solve these type of selection problem. Mathematical form of combination. Selection of items from group of items defined by combination. When selecting m items from the n items, possible combination is given by Cm. N equals n. M. N minus m. Example. 18. Statistical applications in environmental sciences. Possible combinations of selecting 2 marble from a bag of 6 marble equals 6. 2, 4, equals 15. Question 1. 1 unbiased dice is thrown. Find the probability. A. Dice shows 5. B. Dice shows even number. C. Dice shows odd number. Answer. 1 unbiased dice is thrown randomly. Possible outcomes are 1, 2, 3, 4, 5 and 6. Mathematical approach is used to find probability for given event A, B, and circa. For an event A. As dice shows 5 only one time. Favorable outcome is 1 and total possible outcomes are 6. Probability of event A is given by P E equals F T equals 1. 6 equals 0.166. For event B. As dice has 3 even number i.e. 2, 4, 6. Favorable outcomes are 3 and total outcomes are 6. Probability of event B is given by P E equals F T equals 3. 6 equals 0.5. For event C. Also dice has 3 odd number i.e. 1, 3, 5. Favorable outcomes are 3 and total outcomes are 6. Probability of event C is given by P E equals F T equals 3. 6 equals 0.5. Question 2. 19. Statistical applications in environmental sciences. Suppose a coin is tossed 2 times. Find the probability of getting head one first time. Answer. Coin has 2 possible outcomes, one is head and second is tail. After tossing the coin 2 times, there are 4 possible outcomes i.e. HH, HT, TH, TT. Favorable outcomes for event are 2 HH, HT, and total outcomes are 4. Probability of getting head on first place or on first coin is PE equals 2. 4 equals 0.5. Question 3. Suppose a bag has 20 with different colors. There are 5 green marbles, 6 blue marbles and 9 red marbles. Let us consider that 2 marbles are selected randomly. Find the probability of getting 2 red marbles, getting 1 red and 1 blue marbles, getting 1 blue and 1 green ball. Answer. Probability of getting 2 red marbles. Bag contains 9 red marbles and total marbles are 20. We are interested in to find out the probability that 2 marbles are selected from 20 marbles and it must be red, so these 2 selected marbles will be from 9 red marbles. Combination will be used to find out probability as P E equals C2 9 C2 20 P E equals 9 2 7 20 2 18 semicolon 20. Statistical applications in environmental sciences. P E equals 9 18 7, 20, equals 0.18947. As bag contains 9 red marbles and 6 blue marbles, to find out the probability of 1 red marble and 1 blue marble. The formula is PE equals C1 9 C1 6 C2 20 PE equals 9 semicolon 8 6 5 2 18 20 equals C2 1 5 20 semicolon 5 6 2 20 9. This module will help learner to understand basic of probability and terminology that is essential for better understanding of the problem. Probability approaches discusses that helps to transform the possibility into numerical results. In this module, main concern is only to introduce you key concepts and simple probability approach and application of probability. Advanced probability problems will be discussed in the further probability module. 21. Statistical applications. The objective of this module is to define the process to find out the probability of an event given that external information related to that event is already available, then events must be related to each other. Conditional probability concept is very helpful to solve this type of problem. To solve these problems, the mostly commonly used method that is available in the literature is Bayes' theorem. In 4. Statistical applications in environmental sciences. This module, the concept of Bayes' theorem and method of Bayes' theorem with examples will be discussed in detail. 2. Introduction. Let us consider, there are two bags 1 and 2. Bag 1 contains 3 blue marbles and 4 green marbles and bag 2 contains 5 white marbles and 2 red marbles. One marble is drawn randomly from one of the two bags. The probability of selecting a bag is 1/2. The probability of randomly drawing a blue marble from bag 1 is 3/7. Probability of randomly drawing a green marble from bag 1 is 4/7. Probability of randomly drawing white marble from bag 2 is 5/7 and probability of randomly drawing a red marble from bag 2 is 2/7. One bag is chosen at random and one marble is drawn at random from it. Now the probability of drawing a red color marble from second bag is available. If we are interested in drawing a marble from a bag 2 given that the color of the marble drawn is red. From above example, one can observe that problem has some basic information given in terms of probability. Basic information is used to find conditional probability as a new information and this new information is used to find basic information in the new form. In this example, basic information given in terms of random selection of bag and marbles, new information is the probability of drawn marble is red given that selected bag is 2 and a new form of basic information is the probability of red marble comes from bag 2 given that marble is red. These type of problem-solving technique method was given by a famous mathematician Thomas Bayes in 1763. The formula developed by Bayes for the solution of reverse probability is known as Bayes' theorem. Bayes' theorem is used to find the probability of reverse probability of the events with respect to additional information. Bayes' theorem has wide application area. The most specific application area is the backbone of statistics, i.e. statistical inference and Bayesian inference. In this module, our main purpose is to give you brief introduction of this topic with more and more examples. The basic idea behind keeping this module as simple as possible so that one can understand the topic in an easy manner. 3. Some preliminary results. In this section, some preliminary results will be discussed. These results are very helpful to understand Bayes' theorem as well as its application part. Partition of sample space. 5. Statistical applications in environmental sciences. S. Sample space is a set of all possible outcomes of a random experiment. Sample space is mostly represented by S symbolically. Suppose a random experiment is conducted for selecting a bag out of two bags denoted as 1 and 2 respectively. These bags contain marbles of different colors. Then the sample space is, there are two outcomes E and F. E represents for bag 1 and F for bag 2. S equals 1, 2. E equals 1, F equals 2. This sample space S can be divided into two partitions E and F. Partition E and F jointly represent whole sample space if it is mutually exclusive, exhaustive and non-negative. Similarly, if a sample space S can be partitioned into n outcomes, these outcomes are events. These events represent the partitions of the sample space or jointly represent whole sample space if the partitioned event is exhaustive, mutually exclusive and non-negative. The mathematical representation of the partition of sample space. Suppose E1, E2, En are n events of a random experiment. Sample space is given as S equals E1, E2, En. Events are partition events of sample space if I exhaustive. E1 union E2, union En equals S. E mutually exclusive. Ej intersection Ek equals empty set for all j, k equals 1, 2. N. E non-negativity. Pej is greater than or equal to 0 for all j equals 1, 2. N. Venn diagram representation of the partition of sample space. E. 6. Statistical applications in environmental sciences. Figure 1. From Figure 1, we can see that the event A is represented through the mutually exclusive and exhaustive events EI, I equals 2, 3, 4. These events are part of the partition events of sample space S. One can also observe that events EI, I equals 1, 2, 5 jointly represent the whole sample space. Hence any event can be represented through EI events due to its mutually exclusive, exhaustive property as well as non-negative property. Theorem of total probability. 1. E2. En are the partition events and has non-zero probability of happening. The probability of happening an event A is associated with EI, I equals 1, 2. N as PA equals PE1 PAE1 plus PE2 PAE2 plus PEN PAEN. This is known as theorem of total probability. Proof. As EI are mutually exclusive and exhaustive events, so any events belong to the sample space can be represented in terms of these events. Hence A equals E1 intersection A union E2 intersection A. Union En intersection A, 1. Also if an event does not belong to some EI then intersection will be empty i.e. A intersection EK equals empty set for some K. As events EI, I equals 1, 2. N are the partition events then there must be some events that has non-empty intersection with the event A. A intersection EJ does not equal empty set for some J does not equal K. Now take probability on both sides of 1 we get PA equals PE1 intersection A plus PE2 intersection A plus PEN intersection A. 2 as EI are mutually exclusive events so the intersection between partition events are always empty. Hence the other terms will vanish in the above formula. Now from the definition of conditional probability, we know that PAEI equals PA intersection EI. PA intersection EI equals PEI PAEI. Now put the conditional form in equation 2 we will get PA equals PE1 PAE1 plus PE2 PAE2 plus PEN PAEN. Hence proved. 7. Statistical applications in environmental sciences. The total probability theorem has played a vital role in the application of Bayes' theorem. So it is essential to understand it before moving forward for the Bayes' theorem. Some questions with answers are discussed in this section regarding this. Question 1. The probability of becoming data scientist of A, B, and C are 0.4, 0.37, and 0.87 respectively. The probability of getting bonus scheme will be introduced if A, B, and C become data scientist are 0.33, 0.7, and 0.57 respectively. What is the probability that bonus scheme will be introduced? Answer. Let E, F, and G denote the event that A, B, and C become data scientist respectively, and X denotes the event that bonus scheme introduced. E, F, and G are partition events because they are exhaustive, mutually exclusive, and non-negative. In other words, if A will become data scientist, that has no relation with whether B or C will become data scientist. Similar, if B will become data scientist has no relation with whether A or C will become data scientist. Also, C has no relationship with A or B qualification for becoming data scientist. Probabilities are given by PE equals 0.4, PF equals 0.37, PG equals 0.87. As bonus will only be paid if that person will be data scientist. So being a data scientist is a condition for getting a bonus scheme. Hence the probability of introducing bonus scheme given that E, F, and G become data scientist is given as PXE equals 0.33, PXF equals 0.7, PXG equals 0.57. The probability of introducing the bonus scheme by using total probability theorem is given by PX equals PE plus PF PXF plus PG PXG. Px equals 0.4 asterisk operator 0.33 plus 0.37 asterisk operator 0.7 plus 0.87 asterisk operator 0.57 equals 0.8869. The probability of the bonus scheme will be introduced as 0.8869. 8. Statistical applications in environmental sciences. Hence we can see that the probability is very high. This means that if all three, i.e., A, B, and C will become data scientists, then the chances are very high for introducing a bonus scheme. Question 2. A letter comes either from Prague or Kerala. On the paper, just two consecutive letter Ra appears. What is the probability that two consecutive letter visible on the paper is Ra? Answer. Suppose E and F two events. Event E denotes the event letter comes from Prague and F denotes the event letter comes from Kerala. Event X denotes the event two consecutive letter is visible on paper or Ra. Find the probability of X by using theorem of total probability. E and F event are exhaustive, mutually exclusive, and non-negative. E and F are partition events of X. Probabilities are given as PE equals PF equals 1, 2. As letters come from above, two words are equally likely. Also, PXF equals 1, 5. PXE equals 1, 5. Using the theorem of total probability for two events, the formula for the event X is given as PX equals PE plus PF PXF. PX equals 1, 5 asterisk operator 1, 2 plus 1, 5 asterisk operator 1, 2. PX equals 2, 10 equals 0.2. Hence the probability that two consecutive letter Ra visible on paper is 0.2. Question 3. A computer disk manufacturer company produces computer disks. Let us consider three computer disk manufacturer companies are Western Digital, Seagate Technology, and G Technology. Suppose 9. Statistical applications in environmental sciences. Western Digital produces 60% disks of which 0.25% are defective, Seagate Technology produces 40% disk of which 0.06% are defective, and G Technology produces 25% disk of which 0.5% are defective. Find out the probability that disk is defective. Answer. Let us consider E, F, and G are three events. Event E denotes Western Digital produces computer disk, F event denotes Seagate Technology produces computer disk, and G denotes the G Technology produces computer disk. X is an event that take account of only those defective computer disk produced. As all the manufacturers produced some defective computer disk. So to find out the probability that defective computer disk are produced, one has to apply total probability theorem. E, F, and G are partition events because they are exhaustive, mutually exclusive, and non-negative events. Probabilities are given as PE equals 60. 100 equals 0.6. PF equals 0.4. PG equals 0.25. PXE equals 0.0025. PXF equals 0.0006. PXG equals 0.005. Find the probability of defective computer disk by using the theorem of total probability. Total probability theorem formulation for three events is given as PX equals PE plus PF PXF plus PG PXG. PX equals 0.6 asterisk operator 0.0025 plus 0.4 asterisk operator 0.0006 plus 0.35 asterisk operator 0.005. PX equals 0.00299. The probability of produces defective computer disk is 0.002999, i.e. 0.299%. In this section, we have covered the topic of total probability theorem with examples. In the next section, we will discuss about Bayes' theorem and steps that one has to follow for applying this theorem. 4. Bayes' theorem. Bayes' theorem is considered as the method that is used to update the initial known information using new information. Probability related to initial information is known as prior probabilities. The probability of initial known information after updating is known as posterior probabilities. Bayes' theorem has wide application in every field of study like animal science, zoology, environmental science, biosciences, etc. 10. Statistical applications in environmental sciences. Mathematical formulation of Bayes' theorem. Mathematical formulation of Bayes' theorem is based on the basic partition of sample space and theorem of total probability. Conditional probability is a very useful concept in Bayes' theorem. E1, E2, En are mutually exclusive, exhaustive and non-negative events for an arbitrary A, reverse probability for the initial event given that A is PEJ A equals PEJ PA EJ N area summation PEJ N J equals 1 PA EJ PEJ A equals PEJ PA EJ PA. Note that PE1 PE2 PEN are the prior probabilities, i.e. these events exist before calculating the new probability. These probabilities are available at the initial stage. PEJ J equals 1, 2. N are the posterior probabilities, i.e. initial probability determined after the new information added. We need to find out or determine these probabilities values. Steps. For updating the prior probabilities into posterior probabilities using new information, steps are shown. Step 1, basic information available. Step 2, new information are determined. Step 3, application of Bayes' theorem. Step 4, determine updated basic information. Prior probabilities. New information. Bayes' theorem. Posterior probabilities. 11. Statistical applications in environmental sciences. These 4 steps are applied to solve any reverse probability for any given probability. According to 4 steps, basic information is already available in the data as the happening of partitioned events of any experiment. Second, one has identified the new information based on the prior information. This 2 information are used in Bayes' formula to determine posterior probabilities. Posterior probabilities are the updated version of the basic information under given circumstances of new information. One can easily understand and solve the problem keeping these steps in mind. Some of the examples are discussed for better understanding. Question 4. A person speaks truth 3 out of 6 times. A dice is tossed. He reports that 5 number appeared while tossing the dice. What is the chance that actually there was 5? Answer. Let us consider the following events. E1. Person speaks the truth. E2. Person tells a lie. A. Reports 5. Probabilities of simple events and conditional events are given as PE1 equals 3. 6. PAE1 equals 1. 6. PE2 equals 3. 6. PAE2 equals 5. 6. Probability of actually having 5 on dice is given by Bayes' theorem, i.e. the person speaks the truth given that 5 appears while tossing the dice. PE1A equals PE1PA E1PA, where PA equals PE1PA E1 plus PE2PA E2PA equals 3. 6. 1. 6 plus 3. 6. 5. 6. PA equals 0.5. PE1E equals 3. 6. 1 6. 0.5. PE1E equals 0.5. 12. Statistical applications in environmental sciences. The probability of actually having 5 on a dice is 0.5. Question 5. The punctuality of buses has been investigated by considering a number of bus journeys. In the random sample, 40% buses have a destination of Chandigarh, 60% buses have destination of Patiala and 20% buses have a destination of Jalandhar. The probability of arriving at fixed time in Chandigarh, Patiala, and Jalandhar are 30%, 50%, and 70% respectively. If a fixed time bus is selected at random under consideration, what is the probability that it has a destination of Jalandhar? Answer. Let us consider the following events. E1, bus's destination of Chandigarh. E2, bus's destination of Patiala. E3, bus's destination of Jalandhar. A, bus arriving at fixed time. Probabilities of events are given as prior probabilities. PE1 equals 40. 100 equals 0.40. PE2 equals 0.6. PE3 equals 0.2. Probabilities is new information. PAE1 equals 0.3. PAE2 equals 0.5. PAE3 equals 0.7. Probability of arriving bus at fixed time is given by new information probability PA equals PE1 PAE1 plus PE2 PAE2 plus PE3 PAE3. PA equals 0.4 asterisk operator 0.3 plus 0.6 asterisk operator 0.5 plus 0.2 asterisk operator 0.7 equals 0.56. The probability of bus destination of Jalandhar given that bus has arrived at fixed time. Bayes' theorem. 13. Statistical applications in environmental sciences. PE3A equals PE3PA E3PA. PE3A equals 0.2 asterisk operator 0.7. 0.56 equals 0.25. The probability of bus destination is Jalandhar given that bus has arrived at fixed time is 0.25, i.e. posterior probability. Question 6. A student is answering a question in a competitive exam on multiple choice test. The student either knows the answer or guesses. Let 1/2 be the probability that student knows the answer and 1/2 be the probability that student guesses the answer. Let us consider that the guessed answer will be correct with 1/4 probability, where there are 4 choices to choose an answer. What is the probability that student knows the answer to a question given that student answered it correctly? Answer. Let us consider the following events. E1. Student knows the correct answer. E2. Student guesses the correct answer. Student get correct answer. Probabilities of simple events and conditional events are given as prior probabilities. PE1 equals 1. 2 equals 0.5. PE2 equals 1. 2 equals 0.5. New information probability PAE1 equals 1. PAE2 equals 1. 4 equals 0.25. The probability that student gets the correct answer by using theorem of total probability. The probability that student knows the correct answer given that student gives correct answer by using Bayes' theorem. PA equals PE1 PAE1 plus PE2 PAE2. 14. Statistical applications in environmental sciences. PA equals 0.5 plus 0.5 asterisk operator 0.25 equals 0.625 PE1A equals PE1 PAE1 PA. PE1A equals 0.5 asterisk operator 1. 0.625 equals 0.8. The probability that student knows the correct answer given that student gives correct answer is 0.8. A numerical measure of probability shows the posterior probability using Bayes' theorem. Question 7. A manufacturing company produces a certain type of products by 4 types of machines. The respective daily production figures are: machines daily production in 1000 A30, B50, D26. A product is selected at random from the day's production of the machines and found as defective. A product is selected at random from the day's production of the machines and found as defective. What is the probability that defective product comes from the machine A, machine B, machine C and machine D? Answer. Let us define the following events. E1, product produced by machine A. E2, product produced by machine B. 15. Statistical applications in environmental sciences. E3, product produced by machine C. E4, product produced by machine D. Product is defective. The probabilities of simple events and conditional events are given as prior probabilities. PE1 equals 30. 160 equals 0.1875. PE2 equals 59. 160 equals 0.36875. PE3 equals 45. 160 equals 0.28125. PE4 equals 26. 160 equals 0.1625. Probability for new information PAE1 equals 2. 100 equals 0.02. PAE2 equals 5. 100 equals 0.05. PAE3 equals 1.7. 100 equals 0.017. PAE4 equals 3.5. 100 equals 0.035. The probability of the product is defective. PA equals PE1 PAE1 plus PE2 PAE2 plus PE3 PAE3 plus PE4 PAE4 PA equals 0.1875 asterisk operator 0.02 plus 0.36875 asterisk operator 0.05 plus 0.28125 asterisk operator 0.017 plus 0.1625 asterisk operator 0.035 equals 0.033. The probability of the defective product comes from machine A given that product is defective. PE1A equals PE1 PAE1 PA. PE1A equals 0.1875 asterisk operator 0.02. 0.033 equals 0.114. The probability of the defective product comes from machine B given that product is defective. 16. Statistical applications in environmental sciences. PE2A equals PE2 PAE2 PA. PE 5. Summary. In this module, we discussed 2 important theorems of probability theory, i.e., total probability theorem and Bayes' theorem. One can use these theorems to solve probability problem. Definition as well as key concepts are also discussed. Statistical property theorem like addition probability theorem, multiplication probability theorem and Bayes' theorem are discussed. 0. PE4 PAE PE4 0.16 0.0 Tabular form of all answer in the form of prior and posterior probability. In this section, we discussed how to decide which method or technique will be used to find out the solution. We also discussed that if we have some prior information available, then how to use this information to find out the posterior probabilities.